we have been privileged to work with an amazing team at the international energy engineering firm BuroHappold to take on these questions for the state of Massachusetts. If you don't know them, they did New York's 80 by 50 plan, an amazing heat map for London, and are generally on the forefront of rational, data-informed city and regional planning and engineering. So we asked them to use existing data and careful, reasonable, and transparent assumptions. Where unsure of accuracy, use multiple choices to provide a range of outcomes, and basically answer the question, is this idea worth moving forward? So I'm turning it over to Alex Stelk to share his answer.
Great, thank you. Hi, good morning, everyone. Yeah, so about 4 months ago, let me know if you can't hear me because this is a little wonky. About 4 months ago, we put in a bid for this feasibility study with HEAP to try and answer the questions that Zainab just posed. Really, what's the feasibility of replacing existing natural gas infrastructure with a, basically a geothermal heat pump system? And as she said, this was for the state, for all different building types. And so if you're someone who's in the ground source heat pump space, you're probably saying, wait, what? Like, what are the ground conditions? What are the building types? That's a lot of different stuff. And that was true. And it made it incredibly difficult. And so to address that, we kind of approached this at a very high level, looking across the state at a number of different building types to try and provide a reasonable answer to that question. So the scope of the project was broken up into 5 tasks. The middle 3 were the meat of it. So we had a preliminary analysis when we were looking at Massachusetts as a whole. What are the different types of geology, soil conditions? We were looking at the building types. What was their typical energy consumption? What was the typical density layout of the blocks? And we used that to inform our assumptions. So on one side we had, there used to be more stuff there. On one side we had the site conditions, everything that I just spoke about. And on the other side we had the system size and the cost, which would be informed by the building side stuff, our cost estimates. And they came together to inform what would actually result, if this could actually work. We considered 3 types of geothermal or ground source heat pump technologies. First, ground coupled systems, which basically use the earth, soil, bedrock, as a heat source and sink. We considered groundwater systems, which you use water in the ground, such as aquifers, and then surface water systems. Ultimately, we just did the ground coupled systems because they are, by and large, the most commonly installed systems throughout the state and kind of everywhere in general. You also avoid issues with environmental issues, water contamination, things like that. The permitting process is ostensibly easier with these types of systems. So key considerations. First were the thermal sources. So across the state, if you choose some site, what is the capacity going to be for a ground source system? We looked at land use for a given site, say a street. How many buildings are on that street? What are the size? How closely are they spaced? And then we also looked at building energy consumption. So for all those buildings on the street, how much heating and cooling loads need to actually be met by the system. So in terms of the the thermal sources, there's a fairly wide range of different types of rock across the state. It's mostly granite and metamorphic. That probably doesn't mean anything to you, but it has pretty good thermal conductivity. It's usually located about 5 to 40 feet below the surface. So as we started to calculate things, we used an average depth from this. And then in terms of developed land across the state, a fair amount of it is residential. It's mostly kind of medium to low density residential with a few other commercial and few industrial uses mixed in. So this kind of formed the basis of our assumptions for how we're going to approach this problem, because remember, we're trying to answer a question about a specific system for the entire state. So for the different building types, we developed 5 different building energy profiles, which were based on data for these building types from national data sets, also some state data sets. And then we created these annual energy consumption profiles. We also considered energy efficiency because you're not going to want to install one of these systems if you don't do some sort of energy efficiency retrofit in an existing building, because you'd just be wasting money, right? You want to improve your energy efficiency before you install these things so that you're installing a smaller and thus less costly system. And then we looked at the end use, and this is what gave us our cooling and our heating loads. This is what we had to meet with the geothermal system to make it viable. So the approach, based on the aforementioned kind of like understanding of land use, we developed 4 prototypical street segments that were based off typical building sizes, typical lot sizes, and typical right-of-way sizes across the state, and then kind of more specifically in the greater Boston area, because we could have more concrete data for that. And so for each of those prototype street segments, we applied those building energy profiles to each one of those buildings, and then combined it in a way so that we could account for the coincident demand, right? So if one building is using heating and one building is using cooling, they can kind of cancel out. If they're occurring on different times of the day, then you don't have to size it to the sum of all the peak loads. You can lower it a little bit. So we accounted for that. We assumed that it would be either a closed horizontal or vertical ground coupled heat pump system. We assumed that the buildings would have their own heat pumps and they'd be connected to a thermal loop that was outside and potentially owned by a utility. And this is a key point, we also assumed that it would maintain a seasonal energy balance of about 10%. That means that the amount of heat that you're putting into the ground and the amount of heat that you're pulling out of the ground during the heating and the cooling season is more or less the same. And we did this to avoid thermal degradation, right? So if there's an imbalance between the heating and the cooling, or the heat being put in and the heat being taken out, it could lead to adverse conditions, right? So you're either freezing the ground or you're heating up the ground too much. So this would diminish the capacity of the system and make it work less well, and then also lead to environmental issues potentially. And so we wanted to avoid that. A key thing for that is, if it's a standalone system, there's not much you can do. You can find other sources of heat to kind of put into the ground to balance that out or to take it out. But with this kind of GeoMicroDistrict model, because the systems are interconnected, you have more opportunities to increase diversity. So some buildings may be using heating, some buildings may be using cooling more than others, and that kind of evens everything out, and it allows the system to operate much more efficiently. And then we also looked at cost, which I think is what everyone is probably most interested in beyond the actual technical feasibility. So in terms of installation cost, and again, there was a huge range for what we could find and what was considered. We tried to account for the equipment and labor of actually installing the systems. We tried to provide allowances for design and engineering, the permits and approvals that would come with digging up the street and putting in these types of systems, overhead, profit, contingency, and then also a little bit just to account for the economies of scale. Because sometimes we have price data for like a single heat pump, which is fine, but if you're installing multiple ones, or not a heat pump, a water pump, whatever, you're gonna have some sort of discount. In terms of the rates, so if this were a utility-owned system, they would be charging customers per therm or per MMBTU. We did something that I call like a pseudo rate case, where we assumed a 60-year amortization period, which is basically the life of the pipes themselves, 7.5% return on equity, which is what the utility can take a profit off of, and that's just for the capital investment. And then we passed on the operational cost of like running the circulation pumps to the customer. And that gave us like a rate. So we could kind of compare, you know, if you were a homeowner or a commercial building paying for natural gas now, if this were installed on your street, what would you be paying for that in the future? And again, so this is tough. This is from Mass CEC. This is their small scale residential program, a residential ground source heat pump program. This is the range. There's not a strong correlation between the size of the system and the cost. Now, granted, some of these may be inflated. These are reported and they're to get rebates, to get incentives. So there's some variability here, but this is just to make the point that there's not a lot of good information out there currently about what it would cost to actually install these systems in an individual home, let alone on a street segment in this configuration. And then for the customer cost, again, we assume that they would be doing kind of minor energy efficiency retrofits. So that's insulation, like a white or cool roof in some instances, and then air sealing. And this would just help reduce your heating and cooling loads. We assume there'd be a conversion from their existing heating and cooling system to a heat pump that would connect to this GeoMicroDistrict system. And we also assume that, you know, if you were a residential customer and you had a gas stove, you would need to replace that with an electric stove. If you had a gas dryer in some cases, you would have to replace that with an electric dryer. So we accounted for that as well. But we also did consider the existing kind of incentive programs through Mass EC and Mass Save and applied those. And this is kind of like the overall picture of what we considered. And I'm sorry if it's dense. At the end of the day, the closed horizontal systems really didn't perform that well. And partially that was because you don't have so much room in the street in the right of way to begin with. So it was difficult to size those to an extent where you could actually meet 100% of heating and cooling loads. This is not to say that it's impossible. We purposefully did not consider installations that would go in, say, a parking lot, a park, a private yard. We just focused on the right of way, and to the extent possible, we tried to focus on that 2-inch strip of natural gas utility right of way. You could say that this is, if not the worst case, a very conservative
2 foot.
2 foot.
You said 2 inch.
Oh, no, it's 2 feet. It's definitely 2 feet. The closed vertical actually performed quite well. So this is a best case scenario. And if you remember the thermal imbalance I was talking about, this doesn't necessarily account for that, not yet. But if we just open it all up, we can meet 100% of heating and cooling loads in 2 out of the 3 kind of prototypes that we studied. And for the medium density residential, you can meet 100% of your cooling loads, but not your heating loads. High density mixed use, pretty difficult, but these are also land uses that would be in a place like Boston where you would already face a lot of problems in terms of existing infrastructure in the street. So that wasn't a huge loss. So what does it look like? This is a very generic model of what a vertical system might look like in a utility right away. So we have this horizontal thermal loop with service going to each of the homes or the buildings. And then we have a line of boreholes that are 20 feet on center. And each of those boreholes has a U-shaped tube that goes down and back. And it circulates heating and cooling to each of these buildings. It can coexist with other pieces of infrastructure. Even if you have a separated sewer, it can still fit somewhat easily between these things. So in terms of getting everything into the street, we think it's probably fairly feasible to do. And if as we get into this, you'll see that we have more than this. So we have actually 2 lines, which, as you can see, there's still a little bit of space left over. It wouldn't be this orderly in the real world. I can see Kathy Watkins laughing. But I hope this kind of like clarifies what this would actually look like. So for the medium density mixed use, this was kind of like our best candidate because you had, you know, a fair diversity of loads because you had some retail commercial uses. So you had the cooling that could kind of balance out the heating. Under the balance condition, where we're saying we don't want to even address thermal degradation, we want to be safe. You can meet 100% of your heating loads in this situation and about 60% of your cooling loads. If you were to open it up and interconnect, you can meet 100% of both loads, and you would need to export that heating energy somewhere else so that you can maintain that thermal balance, at least for those boreholes. In terms of the actual energy prices, when we did our faux rate case, the ground source heat pump actually turned out to be lower than the natural gas, at least for residential, and pretty much on par for commercial. And both, as you know, are significantly lower than the cost of electricity. But of course, there are different efficiencies and they're used in different ways. When you look at the actual annual energy cost per building, you still have some savings. So the 2 purple bars represent what the annual cost per building would be for a customer in this configuration. The gray bar going south below the dark line, that's the amount of energy, or that's the amount of money that you would be saving per year with this install. And this is just in terms of energy costs. It's not yet accounting for, you know, what it would take to actually convert or install this system. And so on that note, in that configuration, a lot of the costs for installation are associated with the borehole drilling, which is fairly typical. Sorry, I can't read this too well. Yeah, this is the main cost because, yeah. Be fine. No, there is a point I want to make, but it's not on this one. For residential conversion, a lot of the cost, of course, goes to the heat pump installation itself. Because in this case, we're looking at the balance, you would need to add in that's the next one, sorry, early morning. You would also pay some for the new appliances as well. On the commercial side, this is where the cooling really kicks in, or the lack thereof. So because you weren't able to meet 100% of your heating and cooling loads for the commercial buildings where you had relatively higher cooling loads, you would need to retrofit with some sort of a air source heat pump cooling system that could be integrated with the ground source system to provide kind of that heating and cooling load. And this, even though you're paying more upfront to install a new cooling system, it actually nets out over time because the amount of money that you save just converting to an air source heat pump and getting around the cost you would pay for electricity in a typical air conditioning system makes it less expensive in the long run. So in terms of the actual, return on investment, initial investment, this is an average. We had about $500,000 for the ground source heat pump installation, and that would be taken on by the utility. And with the kind of the assumptions that we had, it would result in about a 44-year payback period. And this is over a 60-year, time horizon. For the residential conversion, after rebates and other incentives, it would be about $5,000 per unit. So that's per condo unit with a 24-year payback. And a lot of that payback would be coming from savings in your electricity cost. And for the commercial conversion, it'd be about $80,000 per building, which works out to about a 37-year payback. So on the other end of the spectrum, for low density residential, when it's in a balanced condition, you can meet 100% of your cooling loads, but only about 30% of your heating loads. Whereas if you open it up again, you would meet both loads, but you'd have a significant amount of cooling energy to export in this case. And this could be taken off by something like an ice hockey rink, commercial, cold storage, anything that would need cooling. So you could interconnect that type of use to that and make the system more feasible. But for the balanced condition, because you're not meeting 100% of your heating loads, you would also need some sort of backup heating. So that's where you would have a natural gas generator, potentially providing heating offsite and managed by the utility. And that would start to represent a little bit higher cost. But on the residential side, still the story is the same. A lot of it is the heat pump installation, a little bit more in terms of new appliances. And in this case, the initial investment is lower at $340,000 with a 22-year payback. And the residential conversion cost is a little bit higher at $7,500 per building with about a 20-year payback. So overall, and this is the summary, this seasonal imbalance is the main kind of issue in terms of capacity. It's not the fact that you can't install enough boreholes, it's that you need to be able to mitigate this issue or else you face those ground condition issues. Like I said before, the closed vertical systems were the most feasible for all systems that we analyzed. And the closed horizontal systems, they could be used in certain conditions, but don't have the kind of broad feasibility that the vertical systems have. In terms of the economic observations, there's a wide range of cost for installation and conversion. We took pretty middle of the road and conservative estimates that don't necessarily account for the different types of existing heating and cooling and distribution systems. They don't account for the conditions you may have on the street, the density of infrastructure, the cost of permitting. So, you know, at the end of the day, there needs to be more information. But that being said, from what we've seen and from our conservative standpoint, it does seem economically feasible. And yeah, the costs are highly sensitive. Finally, we just studied a single street segment. And so we didn't really pick up on the types of benefits and efficiencies that you would get from interconnected systems. So if you have more customers, you increase the rate base and you're able to spread those costs around even more, which would result in lower annual energy cost for everyone that was connected. And then you also get those diversity benefits in terms of running the system at a higher efficiency. So yeah, that's it. I'm sorry I hit you with a lot of information, but yeah, happy to answer any questions.